right, so hello everyone. Welcome back to Radical Mathematicians. What?
Hello, Sydney.
Hello, that's my father, Doug. I'm Sydney. We today are going to be talking about Bhaskara. Bhaskara II, the Indian mathematician from the 12th century. Although his name is not actually Bhaskara II, it's Bhaskara. And the second is just academic shorthand because there's another Bhaskara who we're going to be completely ignoring during this podcast.
Not related.
Not related,
but
no.
They were both mathematicians, but one lived
7th century.
500, 600 years before.
Yes. So, Bhaskara, interesting guy, right?
He was an interesting guy. With these podcasts, we're going to focus on mathematicians that are less well known. You know, if you look at somebody like Gauss or Euler or Galois with his famous life story, there's tons and tons of literature and lectures and maybe even some podcasts about these guys. We're not going to rehash that. So we're going to talk about somewhat less known figures in math. And each podcast we're going to choose one thing about the contribution of that mathematician and try and take a semi-deep dive, like deep as in 15 minutes, which is not very deep. But you know, we're going to also talk about the life and times of Bhaskara.
All right, so Bhaskara.
So let's begin.
He was born in 1114 in Maharashtra, India, and he died in 1185 in Madhya Pradesh. We
don't know exactly where he was born, but he did die in the city of Ujjain, which is famous for its astronomy, which was actually one of the things that separated Indian mathematics, ancient Indian mathematics, from other mathematics. It was very driven by astronomy.
So Bhaskara came from a long line of court scholars in, central western India. And I guess during that time, being a scholar was an inherited tradition. And he eventually became the head astronomer in Ujjain. He was taught by his father, who was also an astronomer. And Bhaskara was a very humble guy. He was like, I only have a fraction of my father's knowledge, and I think that's one of the prefaces to one of his books. So Bhaskara was part of the classical period of Indian mathematics, which is generally considered 400 to 1200. So he's at the very end. And basically after him, mathematical development kind of stopped happening in India, or at least northern India, for a while.
Yeah, there was a low period.
Yeah, not dissing Bhaskara or anything. I'm sure he had nothing to do with it. But after that, he was kind of the climax. The Kerala school in southern India did pop up in the 14th to 16th centuries, but that was quite a bit afterwards and in a different area of India. Bhaskara wrote one big work called Siddhanta Shiromani, which translates into the Crown of Treatises, and it's divided into 4 parts. The first one, the Levati, focuses on really basic arithmetic. The second one focuses more on algebra, and then the third and fourth, one is mathematical astronomy and one is the sphere. Most of his work is meant as a teaching work. So Bhaskara skips everything about proving things. He skips everything about how I got where I got to this conclusion. There's no derivations. We only can deduce how he managed to get from one point to the other. He doesn't say, I noticed this and therefore this. He just states everything as a fact. And everything is written in verse, which is also kind of cool. Back then, you couldn't really just buy a textbook. So by having things in schools. Yeah, by having things in verse, people could memorize the rules without referring to the written text. His primary purpose, Bhaskara, was teaching. In his book, he states a rule in verse. He adds a little poetic flair to it, and then he usually gives an example problem and then a solution. He always gives a solution, which math books today really, they're always like, the solution is trivial, and then they make me upset because the solution is clearly not trivial, and I think it's just a conspiracy to make me feel stupid. But no. So Bhaskara was very considerate and gave us a solution guide in his book.
Here's an example. I like this one. A peacock swooped down from its perch atop a pillar, 9 feet high, on seeing a snake gliding towards his hole at the foot of the pillar. The snake was at a distance 3 times the pillar's height from his hole when the peacock sighted him. If they both traveled at the same speed, tell me, quickly, how far from the pillar did the peacock and the snake meet?
How much time is quickly? I don't know the answer to this off the top of my head.
Bhaskara probably could have solved this in 2 seconds, but that is a good example of how he posed his problems. Obviously, this is a problem about, similar triangles or
it takes a second to figure it out.
Proportions, so on.
Here's another one, Dad.
But the whole book is like that. It's many hundreds of pages.
Here's one of his first ones. Friend, tell me quickly the square of 3 1/2, and then the square root of the square, and the cube of it, and the root of the cube, if you know the fractional squares and cubes. Answer, Dad, quickly. Answer, friend.
I'm no Bhaskara.
It's 7 halves. But basically, his entire book is like that. So it's all in meter, too. So there's this thing called anustup meter. I'm definitely not pronouncing that correctly. There's an emphasis on certain syllables. It's kind of like iambic pentameter, but like the Sanskrit version, I think. There's also Mandak Granta meter, where it emphasizes the first 4, the 10th, the 11th, the 13th, 14th, and 17th syllables. His entire textbook is a poem.
And he was considered quite a good poet. This wasn't just taking math and kind of like shoehorning it into verse.
Yeah.
It's considered a work of art.
A
literary work of art.
There have even been verses of his mathematical word problems that have been translated into dance performances in the classical Bharatanatyam style.
Oh, very nice.
I don't know what that is, but
Either do I.
I read it somewhere.
So, do you want to talk about the famous story of who Lillavati was, according to legend?
Sure. So
probably a little bit apocryphal, but good story.
So his first book, the one on arithmetic, is probably the most famous Sanskrit mathematical work, and it's called Lillavati, which translates into beautiful or playful. Supposedly, it was named after his daughter, but Bhaskara never mentions having a daughter. There's no historical evidence that he ever had a daughter, so this was probably just made up by the translator of his work into Persian, I think. The story goes that
there is mention in the text of the Lillavati. I don't know if he ever refers to his daughter, but he refers to Lillavati as a woman. There are like terms of endearment sprinkled throughout the text, but we don't really know if it's his daughter. But it's Lillavati is a name of a woman. That much is clear.
Could
but
be
you're
his
right.
wife.
There's no.
Could be his imaginary.
Yeah, it could
girlfriend.
Could be his imaginary girlfriend. We don't know. He was married.
We do know he had a grandson. He had at least a child at some point.
Yes.
He had to determine his daughter's wedding. So there was a certain time where she was supposed to get married and it would be the correct hour.
This was a superstition.
Yeah.
Right. So there was a particularly auspicious day a lucky day, even a lucky hour where she was supposed to be married. And he predicted this in advance, right?
Yeah, so he was supposed to predict it. And he had a cup. He punched a hole in the bottom of the cup. And he placed it in, I guess, a bed of water so that the cup would gradually fill up through the hole and sink.
And at the moment it sank would be the most propitious moment for her to be married,
yeah,
right?
Yeah. So Lillavati leans over to observe this vessel in the water, and a pearl falls down from her dress and goes into the little cup and blocks the hole, plugging it all up, and it just never sinks. And his daughter is, completely devastated because this was a big thing. And Bhaskara, in his eternal empathy, wants to console his dejected daughter, who now, her marriage is doomed.
The cruel hand of destiny.
Yes. So Bhaskara, in his wisdom, in his fatherly wisdom, is like, you know what? I'm going to write you a mathematical textbook. That will make you feel better. So, I don't know if it worked. But
you're right. It's probably a bunch of nonsense now that you say it out loud. But that is a famous story. Every time you read about Bhaskara somewhere, that story is included.
Yeah, it's one of the weirder apocryphal math stories. There's always one of them. You need to have one for every mathematician. So, Lillavati, what's actually in it?
I don't know which of his contributions are in which of his books, but except the one that we're going to talk about later, the Chakravala, that is in the Bija Ganita.
I'll do this then. He starts off the book just defining the different operations of mathematics. He can cube things, he can square things, he knows what the square root is. He defines infinity, and he realizes that you can't divide things by zero, or you can, but you continue to get a quantity that's divided by zero, and it's like not as legitimate. He says that if you were to divide by zero, you would get a number that is as infinite as the god Vishnu, which isn't quite the definition of zero, but he also realizes that here's his quote. In this quantity also, which has zero as its divisor, there is no change, even when many quantities have entered into it or come out of it, just as the time of destruction and creation, when throngs of creatures enter into and come out of him, there is no change in the infinite and unchanging Vishnu. So that's kind of a poetic thing.
Yeah, so since you bring up Vishnu, that is one of the other things that separates Indian mathematics from other mathematics of the time, or ancient mathematics of the time. The Greeks were very suspicious of anything having to do with infinity, right? This is why they were very suspicious of irrational numbers. Square root of 2 frightened them. But the Indian mathematics, because it was started out, there was a book that way predates Pythagoras and Thales from Indian mathematics called the Solba Satras, and it's from, we don't know the author, but it's from the 8th century BC. This text talks a lot about infinity because it's like a mix of mathematics and religion, and it talks about different kinds of infinity, which is fascinating. It talks about the infinity of numbers, and then it talks about a bigger infinity, which is the infinity of space, and it goes on and on about infinity. So Indian mathematics developed with a kind of reverence for infinity, and I think that's has a lot to do with the fact that they advanced in certain areas much faster than Western mathematics. And that is one of the other things that separates it. And this is why Bhaskara was able to talk about dividing by zero. It didn't bother him that it might be infinity or it might approach infinity. Dividing by zero was just not approached in Greek mathematics.
Was India the first place where zero originated? Yeah, right?
Probably, yeah. But this is way before Bhaskara. There's zero appears as a placeholder first, and then later it appears as a number that you can do operations on. And the in between was hundreds of years. So the modern idea of zero is both. It's both a placeholder and a real number. The first mathematicians who started using the number zero as a number, they actually had to figure out what the rules were. That's why dividing by zero was hotly debated. And Bhaskara actually, that was one thing he got wrong, but he got it wrong for the right reasons. He thought you could divide by zero and you just end up with infinity, and that was okay.
He didn't get it all right, but he got most other things right. It's okay, Bhaskara.
He had a pretty good grasp.
He had a pretty good record.
He had pretty good mathematical intuition.
He realized that he was good with negative numbers. So he realized things that certain quadratic equations had two solutions because the square root of a number could be either positive or negative. He knew all the rules for positive and negative numbers. And actually the negative number sign in Sanskrit was actually a plus sign at the end of a number, which is ironic today. He knew pi. He knew that 22/7 was kind of a crude estimate of pi. He preferred 3,927 divided by 1,250. He knew proportions, so the rule of 3, a divided by b equals x divided by c. You can calculate x. He did not know things like logarithms. He didn't really understand, slices of cones that the Greeks liked. Ellipses, parabolas, hyperbolas. He understood those algebraically, but there wasn't a whole lot of geometric intuition in India at the time.
That's true. The Greek mathematics was very focused on shapes, and Indian mathematics was very much more focused on algebra.
So that's like the very basics that he started with.
Speaking of infinity, he knew an infinite series for the sine and cosine of an angle. That was part of his work in astronomy. He had this famous proof. Now, the Pythagorean theorem was probably discovered in India in the Solba Satras, like 1,000 years, well more than 1,000 years before Bhaskara was born, and it's not unlikely that Pythagoras learned it from that document. Bhaskara actually came up with a new proof. I mean, there are many proofs, right, of the Pythagorean theorem. He came up with a new proof, and in his work, he just draws a picture. There's one famous proof where you have 4 right triangles inscribed inside of a square, such that the hypotenuse of each of the 4 triangles is each one is on one side of the square, and then on the inside it makes a littler square. And what's funny about it is he draws this in his book instead of actually doing the algebra, because it's like 3 lines of algebra to prove that a squared plus b squared equals c squared. He just labels the diagram and he says, aha, or something like that.
Ta-da! The proof is trivial.
Yes, exactly.
No, Bhaskara.
And then he writes down the
Don't
Pythagorean
become
theorem.
those people.
One thing that he knew about was the mean value theorem, or at least the case when the special case that's now known as Rolle's theorem, where it just means that if you have a function that is 0 at 2 different points, then it has to be 0 somewhere in between those 2 points. And he also really understood derivatives. So he made some advances in calculus. And this is like 500 years before Newton. And he also understood that the derivative of a function at its maximum or minimum was 0. And he could calculate this for certain types of functions.
He
mostly for trigonometric functions, which is the functions that are most important in astronomy.
Yeah, so he understood that in the equation sine of y minus sine of x equals y minus x times cosine of x, he understood that if x and y are close to each other, then that equation holds true, which is equivalent to the derivative of sine is cosine.
Right. He knew that.
So I think that's the first time that someone like directly states that. Not sure.
I think that's right. I think that a lot of people have written that he discovered calculus before Newton. I don't think that's quite accurate, but he certainly discovered...
I think that's reaching as well.
Yeah, I think he certainly discovered many of the concepts.
Had something very calculus-like in terms of integration, where he used like the same method as Archimedes to calculate the surface area and the volume of a sphere, where you divide it up into very small areas and then take an infinite amount of small areas and calculate that, which is very calculus-like in terms of... He did some stuff with combinations, so... One of his word problems is how many statues of Shiva can there be with his attributes? The rope, the elephant hook, the serpent, the drum, the skull, the trident, the corpse briber? Don't know what that is. The dagger, the arrow, and the bow held in his different hands. So, and how many of Vishnu with the club, the discus, the lotus, and the conch shell? So he's trying to calculate very basic, combinatorics there. That's one of his example problems. So keep in mind that the translations that we're reading to you guys are English translations, and they definitely do take a lot of liberties. Some of them emphasize more of the mathematical aspect, some of them emphasize more of the verse aspect. And I read, for example, the same passage in 2 different translations, and I would have never been able to tell that they had the same original source. So obviously these things are a lot more poetic in the original, and the English is not doing it justice. There was also, he had a lot of math puns where he tied in, or he named different mathematical operations or aspects and tied them in with more mythical or religious things that obviously there isn't an English equivalent of. For example, I think there's a lot of connotations that we're missing in his poems, like, for example, the word vyakta, which I think he uses as... I'm not really sure what he uses it for, but it's got some religious meaning. Obviously, we're not getting that context when we're reading those verses.
He was a really great astronomer, and he calculated the orbits of all the planets very accurately. He knew the length of the year to within a few minutes, which was way better than anybody else at that time. I think maybe like 9 minutes. He was aware that, and this kind of really surprised me when I read it. He knew that objects fall to the earth because of a force of attraction by the earth. So he knew about gravity, and he knew that the planets were attracted to the earth by gravity, or at least held in orbit by gravity.
He knew that it was shadows that caused eclipses.
Mm-hmm.
And I think the prevailing thought in India was it was the demons Rahu and Ketu. But Bhaskara was spot on with that. And he calculated things like the risings and settings of the planets, the moon's crescents, conjunctions of the planets with stars and each other. Scissor G's? Do you know what that is? I do not.
Yeah, I used to know what that is. Scissor G.
I was reading some of his astronomy work and it just went right over my head. So, for example, I have no idea what the equinoctial shadow of the standard 12-digit gnome, and no idea what that is.
Oh, that's the shadow cast by what do you call it? Sundial. A gnome is the shape of the shadow of a sundial as it sweeps across, as the sun moves and the shadow moves. It creates a curve, right? And that's called a gnomon or gnomon. I don't know how it's pronounced, though. That's the thing. Sundial's obviously very important for an astronomer, right?
Well, not a modern-day astronomer, but I guess Bhaskara needed those. But
I think they had pretty sophisticated sundials, something tells me, in those days.
How do you have a sophisticated sundial? Isn't it just like a stake?
Well, I suspect that it was like extra large, and it was very carefully calibrated so that it was vertical, perfectly vertical, and it was the ground it was on was calibrated so that it was very flat and level, and so that it was extra accurate.
Well, Bhaskara, you have my respect for being smarter than me. I don't know how I would calculate the positions of the planets with just sundials and very basic instruments.
So a Scissor G is when three or more celestial bodies line up in a line in the sky.
Yep, Bhaskara, you are definitely smarter than me. No idea how you would get that.
So do we know anything else about him, his personal life?
I don't think we know much else. I think
he considered Brahmagupta sort of a mathematical ancestor of his, because he actually had the same exact job as Brahmagupta. Brahmagupta lived 500 years earlier, but he was born in northern India, and he ended up at Ujjain as the chief astronomer. Mm-hmm. And Bhaskara was born in southern India, and he also ended up in Ujjain at the center of astronomy and was the chief astronomer. And this is like 500 years apart.
Ujjain. I actually looked up how to pronounce that one.
I did too. It turns out there is no consensus.
Oh.
I heard Eugene and Ujjain. One of the things I learned about...
I would like to apologize for anyone who actually knows how these things are pronounced, because
that's true.
We clearly do not.
We are pretty ignorant about Indian history, pronunciation, so we do apologize. But we're did try to learn as part of our research into Bhaskara. We'd spent a lot of time on the math, though, roughly.
Well, anyway, what did Brahmagupta do? You've been mentioning him a little bit.
A lot of Bhaskara's work was built upon an advanced work that Brahmagupta did. Brahmagupta...
He was born in 628.
Okay.
So,
yep.
like a...
500 years
what's
before?
11 minus 6?
500 years.
500 years.
He was one of the first people to work with the number 0.
Mm.
He was also familiar with negative numbers. In Europe, there wasn't much going on. I mean, there was Greek mathematics, but then there wasn't anything after, say, Ptolemy until Fibonacci, and that's like Bhaskara's time. So there was a lot of advances in India.
I think Fibonacci actually got his hands on one
Yes.
on Lillavati, the
That's-
Persian translation.
That's likely. And of course, Brahmagupta did a lot having to do with trigonometry also because of his astronomy work. So he was very interested in the sine and cosine and pi. And he actually made significant advances in solving, or at least partially solving, Pell's equation, which is what we're going to talk about in a bit. Bhaskara called Brahmagupta the gem of mathematicians. So he had very high regard for him. The Lillavati, by the way, I was reading a little bit about it, and it was used as a textbook right up until the 20th century. In fact, it's still used in some places as a textbook. And
Where?
in India.
Hmm.
And of course, it's, Sanskrit. They're not using Euclid, right?
Who's using Euclid as a textbook in 2021?
Well, I mean, Euclid's book is famous because it was one of the most read and published books of all time, perhaps next to the Bible, right? Because it was like the one.
I thought this was Lord of the Rings had this honor, or Harry Potter.
Maybe now. However, Lillavati, I read, since it's a textbook from the 12th century to the 20th century, or even the 21st century, basically it was widely used until the British came. And then they introduced other textbooks into Indian mathematics. But it may very well have been right behind Euclid's Elements as the most widely read textbook in the world, which kind of blew my mind because I didn't know about the Lillavati. I mean, think of it. Any textbook that's been around for 1,000 years in regular usage.
I feel like
Even
Euclid's
work was lost, right, for 400 or 500 years and then rediscovered. Not literally lost, but not read. And then it became the most, just like required reading. But the Lillavati was required reading if you studied mathematics in India from the year 1200 right up until today, or at least until the British came, whenever that was 100 years ago.
It was not 100 years ago.
Don't know. Whenever that was.
200 years ago?
Yeah, they didn't show up and then the next day they said you have to change the textbooks you're reading. But at some point, the British introduced a new textbook and Lillavati was partially displaced.
Sometimes your dates are wrong,
point.
and I'm
That's
just
my
like,
point.
Dad, you do realize 100 years ago is 1921.
Yeah,
are you secretly older than I think you are? You're like 100 years old and you still think it's 1920.
I like to round. Anyway. So we want to go into some depth about one thing that Bhaskara is known for, and that is his solution to Pell's equation, what's basically an algorithm which he called the Chakravala Method. All right, so Pell's equation is important because it is one of the equations that describes a conic section. So, of course, everybody understands why the equation for a circle is important.
Circles seem important.
You don't have to ask why are mathematicians interested in circles?
Why are mathematicians interested in circles?
Seems kind of like, a basic object.
They should be more interested in the attempts at circles that I draw that are more like lumps.
when you understand that circle is part of a family of shapes that includes ellipses and hyperbola, then you also understand why people were interested in ellipses and hyperbola along with circles, because they're related. They're in a family, which is what the Greek discovered, the conic sections. Now, I don't know if Bhaskara knew about conic sections per se.
I don't think he did.
He did. Pell's equation is basically the equation for a hyperbola.
Which is?
Which is x squared minus y squared equals 1. That is the kind of like the unit hyperbola. If you add coefficients to each of those things, like a coefficient in front of x and in front of y, and you replace the 1 with a coefficient.
So it's like a mutated.
It's a special
hyperbola.
Case. It's a special
It's a
case.
Special hyperbola.
So, of course, hyperbolas have 2 parameters, right? Or 3, depending on how you look at it.
There's an
and
asymptote.
Pell's equation has, right, that's right. So you can, they're defined by a rectangle that determines the asymptotes. And the asymptotes can be at any angle, right? So there's really 2 parameters. And Pell's equation is a special case of a hyperbola. Pell's equation asks the question, if you have a hyperbola, and of course, Bhaskara did not have Cartesian coordinates or anything like that. And he probably didn't even know the shape of that the equation represented. But you're basically asking, if you have a hyperbola and you're picturing it in your mind as lying on a Cartesian coordinate system, right?
Yeah.
So you're picturing a hyperbola.
Which is like it kind of looks like 2 parabolas on its side.
A little bit, yeah. Like it's kind of like a butterfly shape. And Pell's equation asks, when does that curve go through a lattice point? So when is the x and the y, when can the x and the y both be integers and still satisfy the equation? So the actual equation is x squared minus n, which is a coefficient, times y squared. X squared minus ny squared equals 1. And 1 is more or less an arbitrary constant that represents the distance between the trivial point and the origin. So every hyperbola that satisfies Pell's equation, right?
Intercept?
Every single hyperbola that satisfies Pell's equation goes through the point 1, 0. If you change the right-hand side to be 2 or 5 or 10, then it'll go through the point 2, 0, 5, 0, 10, 0. So, but that's not that important. It turns out, while today we know pretty much everything you can possibly know about a hyperbola, mathematicians don't really study hyperbolas anymore. Pretty much everything that can be known is known.
Losers.
The question, I'm sort of simplifying, of course, but whether a specific hyperbola has integer solutions, as to whether that particular curve goes through lattice points and what those solutions are and how many of them there are, that turns out to be a deceptively difficult question. In fact, finding integer solutions for equations in general, which is known as Diophantine analysis or whatever theory, is generally hard.
You've got a little book about that right there.
I have more than one, believe me. And that is still studied, and there are many open questions about that. So you have this hyperbola.
Yes.
Right? And there's a trivial solution where it crosses the x-axis, right?
And you want to find integer solutions of x and y.
You're trying to find the smallest integer solution. That's Pell's problem. That's the solution of Pell's equation. It has nothing to do with like drawing the hyperbola. It really all has to do with finding integer solutions. It turns out the way to solve it is to generalize the problem. If you look at the family of Pell's equations where you're dialing the coefficient up and down, the coefficient n, the coefficient for y squared, the y squared term, if you're dialing that up and down and trying to find some generalization, that approach is a dead end. The Greeks studied n equals 2, right? And they came up, by studying that, they came up with very close approximations, rational approximations for the square root of 2. Because if you do a little bit of manipulation, you can see that you will, solutions will approximate the square root of n for any particular n.
That makes sense.
That's not hard to see. And you can find a series of ever better rational approximations. An infinite series.
By what?
By finding bigger and
smallest...
bigger integer solutions.
Okay. So the first one for 2 would be what? Like x equals 3, y equals 2. And then if you just kept finding solutions with larger x's and y's, they would be better approximations.
Yeah. Yes. Brahmagupta solved Pell's equation for small n. And he used some clever tactics. Bhaskara built on those, but he did not have a general solution for any n. And Bhaskara famously solved the problem when n is 6. It turns out that if you look at different n, let's say from 2 up to n equals 100. So the smallest integer solutions, they kind of bounce around all over the map. There's seemingly no pattern.
I'm looking at the solutions on Wikipedia, right. And there doesn't seem to be a pattern.
Right. And in fact, when you get to a number like n equals 61, Oof. Which is the famous one that was studied by Bhaskara and Fermat.
What is that? A billion?
It's like over a trillion. The smallest integer solution for an xy pair is well over 1 trillion. There's no way he could have solved this by brute force.
Yeah, for some context, for n equals 61, it looks like it's around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 numbers. That's
10 digits.
10 digits. Yeah. That's a trillion? No.
Whatever 10. It is.
What I don't know.
I thought it was a trillion. I thought it was a trillion. Maybe I miscounted digits, but the point is it's a very large integer.
For n equals 63, the smallest is 8 and 1.
Right. So it bounces all over the place, and the next really big number is 109. N equals 109.
Ooh, that's even worse.
Yeah.
15 digits.
Yeah, 15 digits. And then what is 110? Something smaller.
21 and 2.
Yeah, so the pattern of solutions for the smallest solution does seem to be kind of defies a pattern. So it turns out that looking at every different n...
This is scary math.
Yeah, every different n is like a whole different problem. The correct approach, it turns out, is to replace on the right-hand side the number 1 with a coefficient, and usually it's k, right? So you take Pell's equation and you change it from...
So instead of changing around the n, which is what I would think to do, you change around the constant.
Right.
Even though it's supposed to be constant.
Right. Well, you're generalizing it to try and make some headway on the solution.
Interesting.
Which is just a common tactic in different kinds of mathematics. Some people call this generalized Pell's equation x squared minus n y squared equals k, where k is a positive integer, but it's not necessarily 1. And it turns out this family of equations where you can dial k up and down, that family of equations are very closely related. And that is actually the key to solving Pell's equation.
I would have assumed that the general form is a lot harder to solve than the specific. That's very unintuitive to me.
It is unintuitive, but if you do enough math, you'll realize that sometimes the way forward is to generalize the equation and then find patterns, and then you slide back into the specific case. It just sort of works. So now we have generalized Pell's equation. And instead of looking for a pair XY that solves it, you're really looking for a triple XYK. And what Brahmagupta discovered is that if you have two solutions, you don't know what they are, but they're just two solutions, XYK and a different XYK, you have two triples. He learned that you can actually compose them to get a third solution, which is different from the first two. And not only that, but the composed solution is going to be always strictly bigger than any of your first solution or your second solution. So it's like multiplying or composing, if you will. It's not actually multiplying, because multiplying a triple times a triple doesn't really mean anything, but you're sort of multiplying them together to get a third solution. Why this is a big step forward is because right away you know that if you have one solution, you automatically have an infinite number of solutions.
But if K continues to get bigger, how is that?
It's an infinite number of solutions to the generalized equation.
Oh, okay.
Right?
So not K equals 1, just any K.
Right. When I said if you have one solution, you can create an infinite number, you can start out with the trivial solution. You don't have to figure one out.
And Brahmagupta figured out the composition by using properties that the sum of two squares is also the sum of two squares in two different ways, which I think is kind of cool.
I think that's so. If you have two different numbers, both of whom are the sum of two squares, and you multiply them together, it turns out you also get, there's no reason to think if you multiply them together, you would also get the sum of two squares, but you do every time. In fact, you get the sum of two squares, you get a number, the product is the sum of two squares in two different ways. And what that means is numbers that are the sum of two squares form a closed group. So let's do an example to illustrate. Let's say you have two numbers that are each the sum of two squares. 5 is equal to 2 squared plus 1 squared, right? 10 is the sum of two squares, 3 squared plus 1 squared.
Okay.
9 and 1. If you multiply them together, you get 50. 10 times 5 is 50. 50, perhaps unexpectedly, is 7 squared plus 1 squared, but it's also 4 squared.
No, it's 25 squared. It's 5 squared plus
it's 5 squared plus, yeah, that's right. It's 5 squared plus 5 squared, but it's also 7 squared plus 1 squared. So in two different ways, it's the sum of two squares.
So Brahmagupta generalized that identity to get the composition law. And then Bhaskara used that composition law in order to
create the Chakravala.
So someone after found out that you could choose a trivial triple.
You can always choose the trivial solution. The trivial solution, by the way, is just put in either 0 or 1 for y. And then you can kind of back into x.
Yeah, no, but he found out that you can choose another triple that makes each of the quantities in the composed solution all divisible by k squared. And then if you divide out by k squared, instead of getting a larger and larger triple, you get this larger triple, you divide by k squared, and you get a smaller triple.
Right,
and
if you continue to do that, than either one of the original solutions.
Yeah, and if you continue to do that, you can repeat the process until k is equal to 1,
right,
which
infinite
is
descent.
Which is Pell's equation.
So you can you can increase k through composition, and then you can decrease k by dividing through. So you have this, I like to think of it as a ladder, but he called it a wheel. You can slide k up and down. If you find a single solution, you can find other solutions for other k. And so Chakravala means the cycle or the wheel, the method of the wheel. Is that right?
I think
That's
something
how it
like
translates?
that. Chakra means wheel, I think.
So Bhaskara was not that concerned with proving what the solution was. He was more interested in finding the solution. And what he basically did was create an algorithm for finding the solution. And it always worked. What he didn't do was prove that it always worked. The idea of an algorithm that didn't terminate, that might just like go around and around the wheel forever and ever and never terminate, that it was not clear if that occurred to Bhaskara as a possibility. But since he solved this equation for many n and it always worked, suggested to him that it always would work. And in fact, it does always work. But he did not prove that. And it was not proved that the algorithm always terminates until Lagrange. And it turns out proving that it always does terminate is quite difficult. And in fact, he also, as far as I know, his algorithm doesn't absolutely prove that when you do terminate at k equals 1, that you have in fact found the smallest possible integer solution, which is what Pell's equation asks for. But it does in fact do that, but he doesn't prove that it does that. And it was Lagrange who later showed that. And however, Lagrange's method is way more complicated and less efficient. The way Lagrange solved this or proved this was he looked at continued fractions. It turns out that you can show that the solutions to Pell's equations they're truncated continued fractions, representations of square root of n. So for example, for n equals 61, you would write down the continued fraction for n equals 61, or any square root of 61, excuse me. So there's a continued fraction for that. Just like any rational number has a decimal representation that repeats, a repeating word, so to speak, right? So just like every rational number has a decimal representation that repeats, every
rational number,
every square root, if you represent them as a continued fraction, that continued fraction has a repeating pattern in a very analogous way. And that is really the reason.
It's so weird.
It is a little weird.
I don't like it.
That is essentially the reason why the Chakravala method terminates. It turns out that if you take a continued fraction representation of the square root of 61 and you look at all the convergence, which is what happens when you truncate it at each step, the fractions that you get, if you write down the convergence, you get a series of fractions. Mm-hmm. Those fractions are all the solutions to Pell's equation for n equals 61. It's not totally obvious why, well, first of all, it's not at all clear why continued fractions have anything to do with Pell's equation, but...
Well, it has to do with those approximating...
Right.
The Greeks like approximating the square root of 2.
Right, you're approximating the square root of 61 with rational solutions.
Yeah, if continued fractions are related to square roots,
right.
then they're
so
related to Pell's equation.
You can see how it's correct, but the connection is... we're not talking about directly proving the connection, but you kind of intuitively you can see why that's connected, right? It turns out that solving Pell's equation is a very good way of approximating a square root of a number. In fact, it always gives you the best possible rational approximation for any given denominator.
That's interesting.
And these are properties of
know that.
continued fractions that are known now, but were not known in Bhaskara's time. It's known that, for example, I think Brahmagupta knew the square root of 2 to like 6 decimals, and it's probable that he used solutions to Pell's equation to figure that out. That's a very good approximation for somebody living in the year 600. Anyway, we probably oversimplifying, and we probably use some wrong terms, but the basic ideas are there. And
have more confidence in yourself, Dad.
Bhaskara,
What is this?
Bhaskara, even though he didn't do the kinds of rigorous proofs about his algorithm that we would expect today, he probably didn't care, because proving things rigorously was not a thing in that day. He was the first to completely solve Pell's equation for any n.
I read somewhere that it was considered the biggest advance in number theory before Lagrange.
Yeah, probably was. And Fermat, as a challenge to other mathematicians in Europe, put forward Pell's equation with n equals 61. I'm trying to think. Oh, his challenge was solved by a guy named Brunkner. And then Pell wrote a paper about Brunkner's solution. And then Euler mistakenly thought that Pell's paper, he made the mistake of attributing it to Pell. The equation didn't have the name Pell before Euler. So it's misnamed.
So basically you're telling me that not only is it misnamed by Euler, it's misnamed by all of Europe, because it really should be like the Brahmagupta Bhaskara.
Yeah, exactly. It should be the Brahmagupta equation, or Bhaskara equation. But it's called Pell's equation, and it was studied by many, many, many people.
All right, we have to do the closing.
Okay. What's our usual closing? Oh, what did you learn?
What did you learn that isn't relevant exactly to Bhaskara? I mean, we go off tangents all the time.
I have a really good one for this. So there's an Indian rock band.
Oh no.
And I don't know if the name of the band is Supersymmetry or the name of the album is Supersymmetry, but one of the tracks on this album is called the Chakravala. This is absolutely true.
Do you have the lyrics?
I don't think there are any lyrics. It's just sort of like hard techno music. I listened to it. I couldn't listen to the whole thing. It was kind of hard on my ears, but it was like, techno music.
You couldn't fathom the intricacies of Chakravala.
I have a link if you want to listen to this song. It's interesting. It's not bad music, but I was amazed that there's somebody that named a song called the Chakravala. I guess the guy in the band is a big Pell equation groupie. He's either a Pell guy or a Bhaskara guy. I can't tell the difference. What did you learn?
I can't believe you went through the effort of actually finding this and clicking on it.
I'm pretty sure I found it by accident. Googling the word Chakravala. All right, try and beat that.
Well, mine is a little more relevant. I learned that in English, we name numbers up to a billion, right? Mm-hmm. Or maybe a trillion. What's a billion? 10 to the 9th?
Yep.
It's a trillion.
12th.
10 to the 12th. We name numbers up to a trillion, and then we basically give up and use scientific notation. Bhaskara, in his book, names everything up to 10 to the 17th, which is a huge number for someone in 1100 to be concerned about. And I learned that Sanskrit has names for decimal places up to 10 to the 140th, which is absurd. Do you know how many atoms there are in the universe?
No.
It's not 10 to
but
the
I did read about
140th. It's 10 to the 80th. So Sanskrit really went overkill with naming these numbers. You will never need to know a number that big.
This is another reason why Indian mathematics was very comfortable with very large numbers and even infinity.
Do you want to do a goodbye?
Sure. Goodbye, goodbye, goodbye. The end.
Okay. Goodbye.